So, let us get on with the section 3 of our first part of our course, where we are kind of reviewing the basic background on RISC-style processing of basic computer architecture. Now, just if you recall, we have discussed about the 5-stage RISC pipeline. Next, we have discussed about the memory hierarchy that is prevalently popularly used. Now, we have just covered the basics here, and after that we are trying to figure out what are the different techniques that are popularly employed inside microarchitecture in order to exploit the parallelism that is present while instruction processing. Because although we started with the basic background that I have a basic 5-stage RISC pipeline, in modern microprocessors the pipelines are far deeper. Moreover, pipelines are hardly parallelized. That means there are multiple parallel functional units, or in a you can just simply view it that in a modern microprocessor there are a collection of pipelines which are processing instructions in parallel, although that arrangement is not that simple. So, this whole idea of figuring out how a microprocessor can execute instructions in parallel through pipelining and parallel processing kind of techniques, this comes under this purview of the title that we have here for section 3, which is instruction level parallelism. Now, to discuss about how I can make what are the architectural and compiler techniques using which I can make a microprocessor compute on instructions very fast, let us go back to the basic formula that we had, which was that the basic index of how fast the pipeline is executing is CPI, that is cycles per instruction. So, I have a pipeline through which instructions are flowing starting from the fetch stage up to its completion in terms of register write backs and memory updates. So, we are thinking that let us say a single instruction takes some m number of cycles on the average. So, I would say that the pipeline's performance is m, that is a CPI, that is it takes m cycles per instruction. Now, if I am trying to compute this CPI inside a pipeline execution, what is the actual CPI? That depends on several factors. As we have discussed earlier, considering a multi-stage pipeline where an instructions operation is broken down into several basic stages, and every basic stage is actually engaged in processing some instruction whenever it is executing without any kind of stall, that gives me an ideal pipeline scenario. And inside an ideal pipeline, at the end of the pipeline, I can see one instruction getting completed by every clock cycle. So, that gives me an ideal pipeline CPI for a single pipeline as 1. That means one instruction gets completed in every clock cycle. However, it does not really happen, because as we have seen, there are several kinds of hazards, structural, data as well as control hazards, which introduce what we call as pipeline stalls. So, due to a structural hazard, there can be a stall in the pipeline. That means some instruction sitting inside a stage is not progressing in the next stage in the consecutive clock cycle. So, that induces a structural stall, and similarly there can be data hazard induced stalls as well as control hazard induced stalls. Now, the question is, how are such hazards detected and handled? There are various techniques for that. Now, as we can understand that as a collection of these all different phenomena, we have the actual pipeline's CPI deviating from the ideal pipeline CPI. Now, of course, the calculation becomes more complex when I have more complex pipelines which can execute multiple, which can actually get multiple instructions issued in parallel instead of just having one fetch unit issuing, executing, starting to fetch one instruction in one clock cycle. So, starting from this perspective, let us first discuss what are the classifications of hazards and what kind of techniques are practically used for getting around them by the architecture. Now, of course, for handling hazards, there are well known techniques based on compilers which can also help us to alleviate certain types of hazards. Now, this is also something we will look into. So, I mean the overall point here is that these hazards are kind of impeding the overall performance. Hence, there has to be certain techniques, some of the which can actually help you to approach the ideal CPI. Some of these techniques can be implemented in hardware, so they are architectural techniques, while some of the techniques can be implemented by the compiler, so that it can generate the assembly and corresponding machine instructions smartly enough, so that the architecture can process them with in a more parallels, I mean providing us with higher throughput and get and it's automatically able to exploit higher level of parallelism. So, starting with the classification of different kinds of hazards. So, consider the different scenarios for which we have some data hazards. Now, for that let us start with a scenario that I have an instruction I executing and it's followed by the execution of an instruction j. So, let us consider instruction I. This is followed by an instruction j. Now, what are the different problems that can happen when this sequence is entering the instruction fetch unit followed by instruction decode unit and so on and so forth. So, the first kind of hazard that may happen is what we know as read after write dependencies or read after write class of hazards. So, suppose instruction j is trying to read a source before instruction I writes it. So, let us try and understand how that can happen. So, let me pick up a simple example here. So, suppose I have this instruction I, it is going to perform some operation. So, let this instruction be an addition and it is going to add values from registers R2 and R3 and write it to R1, right. So, overall I have R1 is getting updated with the content of R2 and R3. Now, what if I have an instruction j which is going to use the content of R1 for some purpose. So, let it be a subtract instruction. It is going to subtract the content of it is going to subtract from the content of R1 some content of some register, let us say R8, and put it to R4. So, in terms of pseudocode, if I write, I am trying to update R4 with R1 minus R8. Now, the thing is, I want these instructions to be scheduled like I is to be followed by j, which means when I am executing instruction j, R4 deserves an updated value of R1, right. That means, R1 must have been updated by the previous ith instruction. So, here I have this dependency. Now, coming back to our description of the hazard. So, j is trying to read from some source, and that is some place where I is supposed to write. Now, as we know in the pipeline, I is going to execute the write part in the write back stage. That means, this destination register for I will be updated in the write back stage, whereas the read is going to the read has to wait until this update happens. Otherwise, what can happen is j will incorrectly read the old value. This is something we have discussed earlier also. So, This is a hazard known as read after write hazard. So, unless I put in the stall in the execution of instruction j, it is going to read the older value of source instead of it reading the updated value of the source register. So, this is a read after write kind of dependency. Now, there are several other kinds of dependencies that may happen. So, read after write is the most simple one and also the most frequent one, and we have to understand that unless I am going to delay the execution of j, it is bound to read from the registers an old value, and it is not going to consider the updated value that is supposed to be written by the preceding instruction, that is instruction I. So, this is your example of read after write, and to preserve the semantics of the instructions, in order to force that the read happens only after the update that is to be done by the write, we have to insert the stall. So, this is a data hazard of type read after write. Similarly, there can be write after write. Now, consider this. So, I am always considering that I executes followed by j's execution. Earlier instance I had that j was going to read from a source before I writes the source. Now, let us consider this execution that I is going to write something and j is also going to write something. Now, j tries to write an operand before it is written by I. Now, why it can happen? In a general simple pipeline where register updates will only happen in the write back stage, this problem cannot happen, right? Because instruction I is being followed by instruction j in the pipeline. So, only after I will update its write, only after that j will be updating its write. It cannot happen in such a simpler pipeline, but it may happen in a more complex pipeline where you can have the facility to do write in multiple stages rather than in one stage. So, in summary, this will not happen in simple RISC, but in pipelines that write in more than one basic stage or allow an instruction to proceed even when a previous instruction is stalled. These are the situations where this situation may arise. Now, the other type of dependency is write after read. Now, what is really that? J is the succeeding instruction. It tries to write a destination before it has been read by I. Now, as we have discussed already that I is being followed by j. So, how can really j write before I reading the instruction? So, before proceeding with this, again let me go back to w.r.t type and repeat, because it is related to w.r.t. In w.r.t the problem can only happen when in the pipeline there are multiple possible states where write can actually be executed, and if the previous instruction is doing some write at the later stage of the pipeline, whereas the following instruction is trying to do the write at some earlier stage of the pipeline, then this problem can come. But what about w.r.? Here we are talking about read after write, where the write after read, where the write is an event of the succeeding instruction and read is the event of the preceding instruction. So, read is by I and j is the succeeding instruction trying to do the write. Now, in an in-order pipeline this cannot be a problem. So, we have a new word here. What is an in-order pipeline? Whatever we have discussed till now is extremely in order. That means, I am given an instruction sequence, that is exactly the sequence in which I am feeding the instructions into the pipeline. But the point is, it is not always necessary. There are situations, we will explore them soon, where we will see that instructions may get reordered or instructions execute out of order. Now, when that happens, so suppose there is a smart mechanism inside your microarchitecture which is deciding that okay, I will do a reordering of instructions. It has to do the reordering in such a way that this issue does not arise, that if it is the case that I is going to read some location and j is going to write some location and the original ordering is I followed by j, if I switch the order, then j will be writing a destination and after that I will be reading it, which is not the actual order that is kind of indicated by the original program. So that's again a violation. So WAR is a violation. So we see that write after write and write after read are violations that may happen in certain scenarios. For write after read, instructions have to execute out of order. For write after write, the pipeline has to have the facility that from multiple stages writes are possible. So apart from this, the read after write is a scenario which can occur even in a basic pipeline, but that can be alleviated with suitable stalls. Now what about the other combination that can happen, combining reads and writes? So we have read after read, that is never a hazard, because reads do not update state of any register. Now as we have discussed earlier, that there are various possible techniques in which the parallelism of instructions can be exploited. Some of the techniques are architectural and some of the techniques are also compiler based. So let us kind of review what are the different optimizations that a compiler can do to extract instruction level parallelism. I mean, of course, there are many possible optimizations. We will just talk about one or two of them for a basic motivation. So consider at this point the simple C code segment that we have for a loop. So we have a loop with the loop index down counting from 100 to 0, and all we are trying to do is we are doing a scalar addition. We are adding the scalar value s to all elements of the vector x. Now consider the corresponding MIPS assembly, which is unoptimized. So what do we really have in the MIPS assembly? You have this loop. So we are assuming that the address of this array x, which is storing the vector x, is located in the base address is in this R1 is containing the end address is essentially x100 at the start. That address with offset 0 gets loaded to the register F0. F2 is a register containing the scalar value, that is s, right. So you execute a add.d, basically add for double type values, and you store the content in F4, register F4. So F4 essentially has the content of x100 plus s, right, and then you store the result. Where do you store it? You are supposed to store it exactly at the same place from which you read it, right. So you store it by this instruction exactly at that location. What do you do after that? You are supposed to browse back in the array. How do you do that? So you decrement the pointer by 8 bytes, that is the width of the double type words. So you decrement the pointer, that is the content address content of R1 by 8, and then you branch again into the loop in case you still have data to be processed. That means the base address is inside R2 as long as you are not done. Essentially this is going to contain that, and as long as you are not done, you will be continuously going inside the loop and doing the addition, and in that way you do the scalar addition here. Now what is the issue here? Why do I say that it's unoptimized? It can be considered unoptimized because of the reason we can have an alternate version of the loop where we may end up with less number of instructions to execute. So let's see what's such a solution. So suppose the compiler is provided with this kind of an unoptimized code in the initial part of the code generation process, and then the compiler does some architecture aware optimization, which is this kind of loop unrolling. So what it does is the compiler will, instead of executing, coming back here, instead of executing these many 101 iterations of the loop, it thinks that okay, I will execute this many divided by 4 iterations of the loop, and inside each of the iterations I will do 4 additions. Let us see how the code looks like in that case. So now I have the loop containing a sequence of 4 scalar additions of consecutive locations in the array. So this is the load followed by add and then store, again load of the previous byte followed by add and then store, again the load of the previous to previous byte, that is why my offset is -16, followed by add followed by store. So, at this point I am expecting that from your basic UG background on computer architecture, you should familiarize yourself with MIPS assembly, so that this kind of a program is readable for you, just a reminder here. So, we do a store here again, and then again we do a load at the offset of the 4th position, and then again we do the add and store it back, right. So, I am inside one iteration of the loop, instead of doing one scalar addition, I am doing 4 scalar additions, and then I am shifting back the pointer by 8 times 4 32 bytes, and again executing the loop with the branch if not equal instruction, right. So, what does this really mean? I am doing the same functionality, not a problem. All I am doing is inside one iteration of the loop, I am doing more number of additions. How does it help? It helps because I am executing the branch if not equal instruction less number of times, the previous number of times by 4, that many number of times. So, in every iteration I am eliminating 3 branches and I am executing the 4th branch, right. So, and also I am saving on another instruction, which is the pointer shifting, that is the decrementing of R1, right. So, I have eliminated so many decrement operations and so many branch operations. Why is that a good thing? Because the pipeline takes the equal amount of time for decrementing by 8 or 32, but it just has to execute that many instructions less. It also has to execute the branch if not equal instruction that many times less, right. So, for every branch we know there can be associated stalls and all that. So, all those problems get alleviated. In that way, I have a lesser number of instructions executing, and also if we look at the code here, I mean with lesser number of instructions executing, I have an overall speed up for this scalar addition that is going on, and we have more overlapped execution in the pipeline because the instructions are unrelated. I do not have branches. So, I do not have sequence of branches for each add. So, that makes this execute faster. However, what is the problem with this? In general, there is no problem, but of course, you can always argue that if we follow this process, I can unroll any loop up to any bound. Definitely, that is not a good solution, because programs are considered good for their loopy behavior, right. That means there has to be a sweet spot. That means what is a good unrolling factor. Now, let us consider the side effects or bad things due to unrolling. Your code size is increasing, right. So, earlier your assembly was this, now you have a much bigger assembly to be executed, right. You have loopy behavior, but inside each iteration of the loop you have more work to do. So, your code size increases. That will create more number of instruction cache miss, because you are now fetching more instructions from the cache. I mean, since your code size has increased, so there will be more number of misses, and you are fetching more instructions of basically which are the same instructions, but they are duplicated and stored in separate memory addresses, right. So, that is definitely a problem. And the other problem is, when this code is executing, you have more number of live values. So, more registers may get engaged due to renaming and other things, which we will cover later, and that creates a problem called register pressure. So, these issues are there, which will be clear of course, as we progress through a bit more of content, but just to make a point that one should not think that okay, unrolling is a smart thing to do, but that means I should completely unroll any program and forget loops. That is also not a good thing because of these problems. Now, coming to some other techniques that also help with respect to exploiting the instruction level parallelism. Now, in unrolling, the help came because we have less number of branch computations. We also alleviated some arithmetic instructions. in terms of pointer increment and decrement. So, with all this that helped in executing the pipeline faster with more overlapped instructions and eliminating certain specific assembly instructions. This is more of a compiler optimization, not something done by the architecture. It is not a hardware optimization. There are, as we have discussed earlier, that optimizations can be done both by the hardware as well as the software. So, what can be a possible software optimization? Let us speak of that. Sorry, what can be a possible good hardware optimization? Let us look into that. So, in modern microprocessors, there is a specific hardware unit called a branch predictor. What it tries to do is to decide whether a branch should be taken or not taken, and we have discussed a bit about this earlier also, that I can say that a branch will be always taken, or I can say that the branch will be never taken. That can be a static kind of prediction. So, because in general for a uniform from a uniform statistics, there is a 50-50 chance about that. However, things can be done with a bit more statistical sense, like we can look at the previous history of branches and decide whether to take the branch or not. Now, by looking at the previous history, I mean, if I think that I will implement a predictor which is much more sophisticated, let us think of the behavior of such a predictor in terms of a finite automaton. So, what can be a very simple automaton? So, consider a simple situation that I am going to decide whether to take a branch or not based on a 1-bit content is a flip flop containing either a 1 or a 0. If it is 1, that would mean I want to take the branch, and if it is 0, you do not take the branch. Now, I want to implement a finite state machine logic to decide on this, and I have the previous history of branches based on only 1 bit. So, suppose the value is 1, which is indicating that the previous branch was taken, and right now if I get a branch instruction, I will take the branch. And if this is a correct decision, then again the state gets updated with 1 only, because the branch was really taken. Now, let the value being 0 denote that although I thought that the branch was taken, but in reality it was not taken. Then I shift to another state, that means I update this 1 with a 0, meaning that this last branch I did not take, right. So, next comes another branch instruction, I will also decide to not take it, and that will be kind of a self loop for this state, denoting that I remain in this not taken state. That means, I do not update the content 0 in this flip flop. Now, following the similar logic and completing this automaton, while my decision is that if any instruction comes, I do not take the branch, and now a branch instruction, I mean if any branch instruction comes, I will not take the branch. Now, if finally it is found that the branch has to be taken, then I switch back to 1. So, this completes the design of a very simple 1-bit, I mean a branch predictor with 1-bit history, is just storing the information about the last branch. Now, so to summarize, this is a 1-bit predictor things can be much more complex, as we can see. So, this is nothing but just a extension of that same concept, and we are now thinking that okay, I have a predictor with a 2-bit, and this is a formal term that you use, you call it a 2-bit saturating counter. Saturating counter for obvious reason that okay, if I take a decision and that decision is reinforced twice, I keep on taking that decision. So, that is what I can, that can be a nice summary. I took the decision that the branch is taken, and then I find that okay, again it is taken. So, now I switch to a state that I call as strongly taken. So, if I find that in a next sequence there is a branch instruction and it is not taken, I come to a state that is called weakly taken. That means still if a instruction comes, I will consider the branch instruction, that is a branch instruction comes, I will consider to take the branch. But then again I see that this was also wrong. So, then again the branch is not taken. Then I come to a state that is weakly not taken. All that is happening is, if I think of the original construction that I just did, I was simply remembering the history of the previous branch and trying to do the same. Now, I am trying to do something based on the history of last 2 branches. So, if last 2 branches were taken, I will definitely take the branch. If the last but one branch was taken, but the last branch was not taken, still I will take the branch, provided I have switched to the weakly taken state from the strongly taken state, and will continue like that. So, you can just encode this behavior, as we can see, in the form of a 2-bit saturating counter, and with this kind of a switching logic, which will actually tell you when or not to take a branch. All again I will just repeat that the way things have started differing now is, in my simpler design it was a 1-bit predictor, in this design it is a 2-bit predictor. I am trying to decide on branches based on a history of size 2. Earlier I was trying to decide on branches based on a history of size 1. So, maybe we will take this up again. Yeah, thank you.